I'm very honored to be pleased to, of course, be working as always with Joe Medosh. Joe is sporting a different look today. I don't know if you can tell. He's updated his profile picture. He must be muted because I'm sure he's laughing uncontrollably with pleasure. But in addition, John Rockwell's on the line. John, are you there?
I am here. Thank you.
Awesome. So John is John's from Zehnder. John's going to be representing Zehnder and telling us, talking a little bit about, what HRVs are, ERVs, talking a little bit about how Zehnder approaches commissioning, which is very unique and I think very interesting, and the main reason why I invited John to join us today. That and also his sunny personality, you can tell by the bright smile, and his soulful bluesy voice.
Exactly.
So Joe, thanks, John, thanks for joining us. John, you want to tell us a little bit before we get started? How about some total disclosure? Let's tell everybody what happened to your throat. Why you're so
sure.
so sultry.
To maintain my sanity, I'm a performing musician. Every Wednesday, I play at a nice little restaurant in the community where I live in Massachusetts, and that, and combined with parenting stresses and life in general, and winter sort of finally leaving Massachusetts and teasing us with spring and summer, I've got some sort of cold or something. So you'll forgive me for my gravelly voice, but it's usually crystal clear. So you can go from there.
Hey, if there's one person in the world you don't have to apologize about having a scratchy voice, it's me. So some of what let's kind of get into the good stuff. What we are really going to be talking about today is, again, what are ERVs and HRVs? What's the difference between them? How do they work? Why are they important? And how are they becoming more and more important? We're going to talk about a little bit about what it takes to commission a new HRV, and like I said, we're really going to kind of dwell on the Zehnder perspective on that, because again, they have a very unique perspective, and they have a process and a protocol that I think is outstanding and needs to be shared. Then after we finish that, we're going to talk a little bit about what types of tools and protocols are best for testing HRVs. And I should have mentioned right in here, I should have probably said something about also exhaust fans if we have some time and if you're interested. So before we get started, John, I want to bring you up next. But before we get started, I want to talk a little bit about some of the products, some of the equipment that you can use to measure flow. A lot of people don't realize that you can actually use a duct tester, so we will talk a little bit about that. If we don't have enough time to fulfill your questions about that you have, we have other webinars online on the YouTube site that we actually talk specifically about that. But we always welcome your questions at the end. So. Of course, you can use a Retrotec flow hood for a duct tester, but you can also use the ASIN flow finder, which is the lightest and most accurate, I believe, in the world. But I just said that, not necessarily the opinion of Retrotec, more of the opinion of Jay West. All right, John. So I want to pass it over to you. Thanks everybody for chiming in. I can see that you can hear us crystal clear, and John, take it from here.
Thank you, Jay. I remember in my days as a college professor, I could easily put students to sleep by simply reading what was on the screen. But I don't really have any other options, considering this is a webinar and I'm not standing in front of you being animated. So we'll try and go through these reasonably quickly. But I think everyone is aware that mechanical ventilation is becoming more and more common, partly because of the result of building codes, partly because of the excitement in the world of Energy Star, Passive House, low energy, high performance buildings. As buildings get tighter and don't breathe the way they used to, we need to still keep indoor air quality, and in fact improve indoor air quality by introducing fresh air. If we do that without heat recovery, we're actually increasing our heating costs and our cooling costs in warm climates. So Zehnder is of a mind that there's a certain kind of ventilation, mechanical ventilation with heat recovery, that is the best. And so I'll just go through these. As I say, houses have become more airtight in the last 20 years. We don't have drafty houses anymore that allow us to stoke a fireplace. It's actually harder in a code-compliant house to get enough drafts to light a fire. And I'm not sure how familiar the listeners of this webinar are in how steep they are in building science and air changes per hour and things like that, but it's critical to building energy conservation. Also, indoor air quality, that third point about how many chemicals can both enter the home just by products that are installed in the home, but that which can actually pass through. Of course, if you live in Brooklyn, for instance, and you leave your window open for ventilation, you're going to be having extremely high levels of carbon monoxide from cars and things like that and buses. So I'm just going to move on to the next slide, if you could. Thank you. There's just a sort of overview of the residential building code and how air changes per hour and making buildings required to be tested with a blower door test to determine their air change rate. Of course, that's not a ventilation rate per se. It's a way of comparing how leaky buildings are, and we know that via stack effect and gaps in the junctions of construction materials, that buildings themselves can actually allow a lot of infiltration and exfiltration too. Those of you who have second floor recessed cans with no insulation or air sealing, more importantly above them, you're going to be losing a lot of energy. Down at the bottom of that slide talks about how in different climate zones, that's what CZ stands for, you have to lower your air changes per hour the colder it gets. So in Massachusetts, in climate zone 5, if you're doing an Energy Star qualified home, you cannot exceed 4 air changes per hour. And that 50, again, I don't know what the listening audience knows, but that 50 refers to pascals, a measurement of pressure, a standardized pressure between indoors and outdoors as created by the blower door. Next slide, please. As buildings get more and more airtight, it's not dissimilar to being in sort of a glass dome. And as you can imagine, with smoking and people and animals and electronics generating heat and things like that, that really has to be evacuated. And we'll talk about the different kinds of ventilation in a minute, but those points that you can see there about the humidity and concentration of CO2s, if you're having a party and 30 people are over, it can get stuffy fairly quickly with people breathing. Volatile organic compounds, which is what a VOC is, odors, allergens, and temperature. Let's move on to the next slide.
Well, actually, if it's okay,
Sure.
Let's see. Were those national climate zones as opposed to CA? What does CA stand for?
Canadian. I'm guessing Canadian.
Mm-hmm. Or California? Is that California? So yes, are those national climate zones or are those California climate zones?
Yes, they are, but I wouldn't be surprised if California had almost all the climate zones in the United States, except perhaps northern Maine and Montana and things like that. I don't know how California's code is divvied up.
Yeah, and then another question on top of that. What is that? What's the little girl? Is she smoking something that's weird? What's she doing? Do you know? Seriously though, here's a good.
Zoom in on that slide.
I got
She's playing the kazoo.
Yeah, that's what I thought. That's the first thing I thought was kazoo. I was like, oh, I guess if you're airtight, it's too quiet. But I do have a question that comes up quite a bit. And thank you, Miss Taylor or Mr. Taylor or Brett. 16 climate zones in California. Wow. Question here. So we've got all these indoor health and comfort concerns that are caused by tight houses. So why do we tighten them if it's going to cause all these health problems, and we have to then install ventilation and go through all this effort and difficulty?
Just to clarify, it's not caused by the tight house. If nobody lived in that house, the house's tightness would have no bearing on it. It's what happens in the house. And this age-old, the old saw of people saying buildings have to breathe. Buildings do not have to breathe, and it's actually terrible when buildings breathe because you're bringing in air with moisture levels that could condense within your wall cavity and not be able to dry out. It's people that need to breathe and creatures that need to breathe in a home, and the ability for people to get that fresh air in the olden days when it was coming in through cracks in construction and no insulation in stud walls. Those days are hopefully long gone, and I love old houses myself, but new houses and houses that need to be retrofit need to be tightened up. And to answer your question directly, the heat loss associated with drafty old buildings is significant. It's phenomenal. It is not necessarily by radiation through the walls or conduction through the walls, although that is a factor, but primarily, in many cases, it's convection, and that is every building will act kind of like, when you go into a skyscraper and the elevators, you can hear the air whoosh. There's a natural stack effect. A chimney won't draw as well unless it has a chimney. A fireplace won't draw as well unless it has a chimney. Stack effect happens, and it's a result of differential pressures and differential temperatures. And in a two-story home, you're going to have exfiltration at the top and infiltration at the bottom, and assumedly in the middle is something called the neutral pressure plane. We try to make buildings airtight and leak as little as possible to prevent BTUs that you've already paid to heat or cool from evacuating or escaping the building. And for those people in cooling-dominated climates, the reverse stack effect occurs, where there's exfiltration around the base of the building because of the density of the weight of cooler air, and infiltration at the top.
What I do want to mention, and what I want to add to that, is the other reason that people don't think about, is the fact that we're just talking about control. So what we're doing is, I think that John did a really good job of explaining that what we're trying to do with our houses to make them tighter is control heat loss, and to control, for thermal control, and as also we're water moisture control and all these things. But we need to also keep in mind that ventilation is a product of the difference in pressure between inside and outside the house. So on different days you're going to get way too much ventilation, and on some days you won't get any ventilation. So the idea is that when they talk about a house needing to breathe, well, what the house really needs is a ventilator. If they really want to talk about it needing to breathe, well, it can't breathe on its own. It needs to breathe. It needs to have it controlled, and that's what we're going to be talking about, is controlling that breathing. So thanks for your input, guys. And John, I'm going to move you to the next slide, if that's okay.
Sure. Yeah. Okay. So when a home becomes airtight, and it does need to evacuate those items that we listed in the previous slide, VOCs and moisture and humidity, there's several ways to do it. The tried and true method that almost everybody has grown up with is exhaust-only ventilation, either by bath fans, well, generally by bath fans, and kitchen exhausts, of course, range hoods. The trouble with exhaust-only ventilation is that if a building is reasonably airtight, exhaust-only is fighting against itself as it tries to get the 80 to 100 CFM that a bath fan may require to be able to evacuate that. If a building has been made quite snug, the fan will be competing against that, as I said. Less common is supply-only ventilation. I actually don't bump into many projects that have only a supply fan bringing in fresh air. But in either of those cases, there's no way of tempering that incoming air as a result of the ventilation process. The next one, called balanced ventilation, is a much better way to manage indoor air quality, because you're not only exhausting from rooms that generally need to be exhausted, like bathrooms, laundries, powder rooms, and kitchens, but you're supplying the places where carbon dioxide can be generated as a result of breathing, so sleeping rooms and things like that, gathering rooms of some kind. And I'm primarily referring to residential projects here. Zehnder mostly makes HRVs and ERVs for residential projects. So if you have supply air and if you have exhaust air, and those are in equal flow rates in CFM, then you're neither pressurizing nor depressurizing the house. I should add that in those previous two options, exhaust only and supply only, if your house is tight and you run an exhaust fan, you are in effect depressurizing the inside of the house, encouraging air to leak in from the outside. And it doesn't take much of a pressure differential unless it's windy and it's offsetting that pressure differential. But on some side of the house, it's going to be exacerbated, and some sides it's going to be mitigated. Air and moisture will come in. So you'll have possibility of condensation on the inside of a dark wall that doesn't get much ventilation, condensation, freezing, rotting lumber, and things like that. Pressurizing the supply-only situation, the opposite is true. It forces out already tempered air, whether that's air-conditioned air or heated air. If you do ventilation and in cold and warm climates, you want to capitalize on the fact that outgoing air that you've already paid to heat has heat in it, and it might as well be used to preheat the incoming cold air, and that's what heat recovery ventilation is. And Zehnder which manufactures the highest efficiency HRVs and ERVs in North America, capitalizes on the benefits of the heat that's leaving the building. You don't mix the air streams, and we'll get into this in just a minute, and hopefully this isn't too repetitive, but if there's some people who don't know about this, the air streams don't mix, but the heat moves just according to the laws of thermodynamics from a warmer place to a colder place. So without getting too much into that, let's go to the next slide and you can see what I mean by that. I'm just going to breeze right through here. That's graphically describing what I just said. A house with exhaust-only ventilation depressurizes the house, allows infiltration through leaks and random leaks, not control. Thank you, Jake. Those are great. Go to the next slide. Yeah. By the way, the other thing about exhaust-only bath fans, how many houses have you gone into and seen that the flex duct connection between the bathroom ceiling and the attic vent has come off, and you're dumping moist air into a cold environment, or it's loose near the roof and it's blowing moist warm air on the underside of cold sheathing and causing frost to occur. These are problems we'd like to say goodbye to. Supply-only ventilation, again, I don't see much of that. Maybe some other listeners know more about that, but outside air is pulled into the home just from the outside, and there's no tempering of it. There are some HRVs on the market that are using ceramic cylinders to store the heat of the outgoing air, and then the fan reverses and uses that stored heat, but that's not what we do, and I'll show you another example. Keep going. Slides. Forward, please. Next slide. Okay. In balanced ventilation, as I said, we exhaust from kitchens and baths, and you provide air to bedrooms. Now, you do not need to ventilate every single room in a balanced ventilation strategy. You start with the exhaust locations, and those places where high levels of moisture, steam showers or odors, and cooking. We extract air from there based on code suggestions and ASHRAE standards or passive house standards if that's what the client seeks. And then you balance that with the same amount of CFM in supply. And generally we start with the bedrooms, and those rooms in between the bedrooms and the bathrooms and kitchens are called transfer areas, and the air does migrate through there. Next slide, please. That is a slide of one of our ventilators, the ComfoAir 350, and the thing that the person's grabbing is called the heat recovery core, and it's the basis of how this system works. It's nothing more than a network of adjacent chambers through which, half of which exhaust air leaves the building, the other half of which fresh air comes into the building. When it's 70 degrees in your building and 0 degrees outside, you have a delta T, a temperature difference of 70 degrees. With some of our units, we can achieve over 90% heat recovery effectiveness, meaning that the cold air, just in the less than 2 seconds that it spends in that hexagonal chamber as it's being sucked into the home, will receive 90% of that temperature difference between 0 and 70 degrees. Of course, that depends on fan speed, it depends upon moisture content and things like that. But what it means is that there's a comfort benefit when that fresh air is being supplied to bedrooms. Instead of being raw, cold, outdoor air, it's now up to 63 degrees if the delta T is 70. And of course, if in your climate zone winters are 35, 40 degrees and you prefer an indoor temperature of 70 degrees, the 30-degree temperature difference, 90% of that is you're much closer to room temperature. So one of the benefits of doing that, since you need ventilation anyway in tight homes, is that you're not bringing in cold air that increases your heating load. So one of the benefits of building tight and ventilating right is that you can downsize your heating system, whether it's hydronic or forced hot air, and the load on the building is significantly smaller because we're thinking about the building as a whole system. A tight envelope, good windows that allow solar radiation to come in, mechanical ventilation to capitalize on the waste stale air that's leaving the building, and a reduced heating system. Next slide. There's a sort of a diagram. Our website, ZehnderAmerica.com, has some fascinating animations of how the cold molecules enter the building and go through the heat exchanger and then get distributed to the room. So I strongly recommend those of you who are interested to go to ZehnderAmerica.com. Now, we talked a little bit about HRVs, and everybody can bandy that about, and a lot of people say ERVs, and I understand it has something to do with moisture. The official name for that is called an enthalpy recovery ventilator. The difference between the two is said right there. It's an HRV system that also can pass moisture between the two airstreams. It means that the heat recovery core is made of a material that will allow moisture to pass through it, as well as to be able to conduct heat from the warmer to the colder airstream. ERVs are very beneficial in climates that are generally quite humid, whether they're coastal communities or the deep south, where the introduction of moist air into the home would increase your dehumidification requirements. So what an ERV can do on a cold, clammy evening is bring in cool air. It will be warmed by the outgoing airstream, the heat associated with those airstreams, but the moisture in the incoming fresh air will be transferred to the outgoing airstream. So it does not increase your humidity levels indoors. You'd also use an ERV in a very, very dry climate, a mountainous climate or desert climate, where it's very dry outdoors, and bringing in air of a very low relative humidity would create unpleasant circumstances for your skin, for your furniture. And so by directing the moisture from the outgoing airstream, where relative humidity is generally higher on the inside because of people and breathing and plants and moisture generated by cooking, that moisture can be transferred to the incoming airstream. Next slide, please.
Okay, John, we did have a question,
sure.
And I think you covered it, but we did have a question from Florida about how will it cost to deal with fresh, hot, humid air being brought into the house? And I think you covered that when in your discussion here of enthalpy, correct?
I come from a cool, heating-dominated climate, but if you think about it, if you want an indoor temperature, let's say you set your air conditioning at 70 degrees, and that's your interior ambient temperature, and in Miami it's very high humidity and never really over 92 or 94 degrees, the delta T there is 24. A heat recovery ventilator will bring that outdoor temperature down by that up to 90%. So if your delta T is 24, 10% of that is 2.4 degrees, times 9 is 18, whatever that is, you're quite close to your incoming air temperature. And you really want to use an ERV in humid Miami because the incoming moisture, most of that will be directed, not all, it's physically impossible to transfer all of the moisture and all of the heat, but we're the most efficient, as I said earlier. The moisture coming into the building will be directed into the outgoing airstream, all in the core of the ERV unit. But if you did not do that, if you left your windows open and relied on ventilation that way in Miami, well, your air conditioner would be running crazy all the time, dehumidifying. So there really is a benefit in moist climates to an ERV. And in fact, we're seeing ERVs creep north in terms of providing both a heat recovery benefit and dealing with moisture. The dog days of summer, even in New England, are times when an ERV can be beneficial. And if there isn't a big moisture difference, well, then it's no problem. You're just not capitalizing on the benefits of an ERV. I hope that answered the gentleman's question, or whoever it was.
Yeah, does that? And we also had a question too about ERV in a humid climate from a cooling application. I think did that cover that question too? Does that cover both your questions? So I guess the question is: so a drain for condensation is not needed.
Interestingly, Zehnder is a European company. It's a Swiss-owned company, and our products are made in Holland and Germany. In Europe, they do not specify a trap or a drain for an ERV because so much of that moisture is recovered. My theory is that while that's true, it's short money and good insurance for, in our case, a $50 really beautiful P-trap, a waterless P-trap that has a little ping pong ball through, and there's no condensate in the line. You still have air tightness in the HRV, but that if you do have an accumulation of moisture, which is rare and unlikely in ERV, that is in excess of what the core can hold, you at least have that extra. So now, if it becomes a gigantic problem of having to run a line to a indirect drain or a condensate pump and things like that, we can reasonably confidently say you don't have to use one, but I like to spec one in our systems anyway.
All right. Thanks, John.
Yep. We think about energy conservation a lot of the time, but really, depending on the application, it's not the primary achievement of having mechanical ventilation. If you live in an urban environment where you just don't want to have your windows open all the time, mechanical ventilation with heat recovery can be a very useful thing and still have a good quality of life indoors. So that slide on the left shows a jetliner landing at a nearby airport and the kid reading by a window. You don't have to have the windows open for fresh air. In fact, in our installations in Manhattan and Brooklyn, of which we have many, many, it's remarkable to go from a sort of grungy streetscape into a really fresh environment inside. Of course, you're probably changing your filters more frequently because of the urban grit and the outdoor air quality. Of course, mold has become a big issue. Back in the days when people were just slapping on polyethylene on the inside face of their basement walls and not realizing that air is migrating into their wall assemblies and condensing and having no way to get out because the poly is impervious to moisture, vapor impermeable. That's where mold builds up. Now, that isn't always going to be solved by mechanical ventilation. Depends on the moisture conditions of the wall assembly and the ground outside and the interior air. But if airborne circumstances are contributing to the mold, an HRV and ERV can certainly help mitigate that. Next slide. So there's a quick overview, a kind of diagram of in the topmost part of the building, Jay, if you can use your laser pointer, you can see a ventilator unit, whether it's HRV or ERV, does not really matter. And there's 4 pipes associated with that, 2 of which connect to the outdoors, bringing in fresh air, one exhausting the stale air. Upstream of those is the heat recovery core, and then the supply system. You can see those bluish-greenish tubes going to a bedroom in that case, and then following along lines into a living space. And that last line is going into, I guess, a kitchen. Then Jay's got his cursor on the yellowish line, extracting from moisture sources. This sort of generic slide. We don't actually provide ventilation for your range hood in North America. Zehnder has a solution in Europe. We haven't brought that over here just yet. The codes are a little bit different here, so we can just move on.
Actually, John, if it's okay, I think this is a good point to, before we start to talk a little bit more specifically about some of your solutions. We had a really good question that I was waiting to pose until we got to this point. So I'm going to read it. Can you see the question, John? It's from Mr. Sharp. Because I can read it for you if you like.
Why don't you do that? Because I maximized that window, but it doesn't show the entire window. It says something that ends in interchangeable cores, I think.
Yes. So the question is,
the full question. Yep.
When appropriate, it would be good to get comment on the new ANSI ResNet testing procedure that has a new category from previous Chapter 8 for a testing device called passive flow hood. That's in quotation marks. And Joe, I think you might be able to speak to this too. Are anemometers with capture hood in these categories? I assume yes. And in that standard, those devices can only be used in multi-branch systems when pressure in hood does not exceed 8 pascals. In your experience, will that be an issue with HRVs, ERVs, with those devices?
Okay, so the part of that is that the main passive device that's used for a lot of people is the Energy Conservatory exhaust fan flow meter, and in and itself, it has the limitation of 8 Pascal. So I think some of the requirements were designed around that device in general. So Colin and I actually reviewed this just recently, and we're going to try to see if we can't provide one more series of feedback on that, because some of the devices that we have, or if you make your own device, there doesn't have to be a limitation on that. And we understand why that was 8 versus the other ones were 5 Pascal limitation. So some of you may have no idea what we're talking about, but it's the ResNet as a standard about how to test exhaust fans, and they have a power or a passive system. So the passive system has these limitations that your numbers should not read above 8 pascals with the device, otherwise it could be a false reading. So that's really only particular for the device itself. I think the manufacturer allows you to go higher. It should be permissible. So I think there is some debate about that kind of detail, if that helps.
Joe, did you see there that there's a couple of follow-up comments here? You said the exhaust fan flow meter is not in the same category in this new standard, and that the flow meter is not allowed at all in multi-branch systems.
So yeah, it's. I think I need to brush up on a few details about that. I have some other distractions in front of me with what we're trying to conquer with the webinar. So I apologize that it's not my total strength, but it's something I reviewed recently. So I will review some of the comments that are on here, and we try to reply to people back to that. So I do know that it's under review, based on my understanding. So it's not a final document yet either.
So up to that point, so I see there's another follow-up question, but I will say up to that point, let us do some research and get back to you on that.
So I copied this slide from our cousins in England. So that new acronym MVHR, that's mechanical ventilation with heat recovery. So don't be intimidated by that. You can read that. It's a pretty straightforward description. I just wanted to be able to show our 4 units that we use around North America, and ranging on the left from our ComfortWare 200, which is the 200 refers to the flow rate in cubic meters per hour. So its maximum flow rate is about 116 CFM, all the way up to our far right-hand unit, the ComfortWare 550, which clocks in at about 325 CFM. Those are the maximum fan capacities when we design a system, and I won't go into great detail about this, but when we add up the required exhaust rates in a home and balance that with the same amount of supply, we want that number. And in a standard house, it might be between 96 CFM up to 144 CFM. Bigger houses can get up to 168, even 192 CFM if there's a lot of plumbing locations. But we generally want that target number to be the middle range of any of our units. So the ComfortWare 550 on the far right would probably work just perfectly with a house that had a required constant ventilation rate of between 144 and 168 CFM. We do actually pair the units in much larger homes. You can do that. That unit second from the right actually is our HRV with the lowest capacity. That's our ComfortWare 160. And along with the one on the far left, both of those can be mounted to a ceiling and work in apartment buildings, and go above a lowered ceiling in a bathroom, and the ducting works quite well that way. So let's move on to the next slide. I just want you to see what our ventilators look like. Another description of how balanced heat recovery and with mechanical ventilation with heat recovery works, where fresh air comes in, but it's always going through the heat recovery core, getting as much heat as possible from the outgoing waste stream. Next slide, please. Okay, so we're not in my world anymore. I don't recognize this slide, but I know there's more that I can get to in a minute.
Yeah, so I think that this is actually a good opportunity. I think we've done a really good job here so far. It looks like thanks to everybody that's listening in. I think we've done a good job of getting people ready for it. Let's actually talk about commission. Excuse me. Let's talk a little bit about commissioning. Okay, so John, what I want to do now is kind of pass it or kind of I guess cue you to talk a little bit about commissioning and how Zehnder approaches that, because I think I did quite a bit. I think I spoke quite a bit in the beginning about how you guys are unique and how it's I think very important for you to explain.
Sure. Thank you. So the fact that we're talking about commissioning is heartening to me, because I think so many of our systems in our homes and other buildings aren't really commissioned to work properly. Of course, it's duct blasters and things like that. It's great. But what's important to understand with a balanced ventilation system is that you can install it and you can get the machine up and running, but if there's no system in place to make sure it's operating properly, you could still run into the same problems, maybe not to the same degree, of what happens when you use exhaust-only ventilation or supply-only ventilation. That is to say, there's two fans in our HRVs, one for supply, one for exhaust, and they're both set to work at the same speed. And of course, when you turn them on, if the total number of duct runs for supply is shorter than that which is for exhaust, you're going to have a buildup of pressure in the exhaust lines because the lines are longer, there's more static pressure. So in fact, you'll be creating an imbalance in that. And so it's vitally important to match the total number of supplies and exhaust to make sure it's balanced. And of course, that's what commissioning is. Zehnder is, as far as I know, the only ventilation manufacturer in North America that, as part of its quotation process to sell our products, includes a commissioning fee, which used to send myself or my colleague Aubrey traipsing all around the country balancing systems, but we've grown so much in the last 4 years that we are now working with independent third-party commissioning agents, one of whom has already contacted me during the webinar, and to train according to how we like the systems to be commissioned, to go out and measure the flow rates at each exhaust point and supply point, and then calibrate the system so that at each of the 3 fan speeds, 1, 2, and 3, the system is in balance at all times, and this house is neither pressurized nor depressurized. To do that, we have a pre-commissioning checklist, which you can see here, which we require customers to complete and send back to us as they request a commissioning. And so, of course, when our commissioning agent shows up, and maybe many of the listeners have shown up to do some system testing and found out that the system's not even running or up and running, and they become a installer rather than a commissioning agent. But you can see each of those points. You have to make sure that the unit is fully installed and connected to the ducting system. Before I go down this list, I want to point out that the other thing that's unique about Zehnder systems is that while we can connect to existing ductwork systems for forced hot air and AC systems, it becomes a complicated dampering scenario to size those ducts for both very low velocity or low flow rate ventilation rates, and also the higher velocity, higher speed rates for heating. So therefore, one part of our system, which I did not show in this because it isn't relevant to commissioning really, is that we have all home runs that go from a silencer and manifold system at our HRV and ERV to the rooms that they serve. So it's a flexible, corrugated, food-grade plastic tube that can sneak in and around eye joists or through web joists, or you can cut holes through lumber. They make their way to the room that they serve, and the registers go either in wall cavities or in floor joist cavities above or below the space. And therefore, you're not getting trunk and branch systems. Now, there's a qualitative difference between that because you're not getting noise echoing from one room to the next, and it's a very quiet system and then really a beautiful system. In fact, they're almost inaudible when they're running. And so, so the ducting system is unique in that it's a home run and sort of an octopus coming out of the top of the HRV and going to the exhaust locations and to the supply locations. It's much easier to commission that way, in my opinion. The unit, as many of you, if you're doing ResNet or other sort of commissioning checklists, this is probably not a whole lot different, but we have to make sure that ours is connected to power and running. We have our own controls. Our whole system is we have everything from the HRV to the distribution system to the controls to the external grills to the integrated insulated intake and exhaust pipes. So everything in the system has to be in place. You can go to the next slide. Basically, it's a walkthrough that you can go through with this checklist, and to begin calibrating the system, you go around and measure the flow rate based on the intended flow rates that the designer, me in a lot of the cases, has called out. Without getting into a description of all these ASHRAE standards, we basically start with 36 CFM of exhaust at a kitchen, 24 CFM of exhaust at a bathroom that has a shower in it. If it's a master bathroom and has a separate toilet room with a closing door, we put 12 CFM of exhaust there. And then also separate powder rooms and laundry rooms get 12 CFM of exhaust. So all of you who live in a home right now could calculate the required continuous exhaust flow rate by simply adding 36 for your kitchen, 24 for each of your bathrooms and 12 for any separate laundry rooms or half baths, and get what that rate is. Oftentimes it lands between 84 and 120 CFM, or a little bit more, but we do that in increments of 12 CFM because that's what our tube is rated for continuous ventilation. Once you get that exhaust rate, you match that with supply rates, and as I said earlier, you populate bedrooms with supply registers, and it's just a matter of going around and checking it at each of the fan speeds and making sure that you can adjust the flow at the diffusers to get the flow rates that you need. Our system, we like, as I said before, to run continuously at about 50 to 60% of its maximum capacity. That capitalizes on high electrical efficiencies. The faster the fan runs, the logarithmically more electricity it uses, and also static flow is higher at faster velocities. And so we'd like the system to not run too quickly. And so you're getting very low flow rates in spaces that such as 24 CFM to a bedroom. And depending on the precision of the instrument that's doing the reading, we rely on those to calculate and to adjust the system to make sure it runs at those rates. It might be useful to talk about Retrotec devices and the ASIN device, because sometimes flow rates need to be adjusted with a lot of precision. We're not dealing with high velocity heating systems. We're really trying to deal with 12 CFM in a bedroom, and that's almost undetectable sometimes to the human hand. You might need a piece of tissue paper to actually see that it's flowing. So you add up 6, 8, 10 exhaust points, and if each of those is off by 1 or 2 or 3 CFM, you can wind up imbalance, having a system out of balance. So maybe Jay or Joe could discuss more precisely some of the devices that you guys use. I've used Retrotec before, of course, but I'm no expert.
Thanks, John. Two questions that I think you might be able to speak to while I switch over. One is how much time is expected to commission a system?
It depends on once you're up and running, and really you don't have to go up and down 6 flights of stairs in a Brooklyn townhouse, and it's a 1 or 2 story house. So you can certainly half a day seems like a reasonable expectation all by yourself. It gets a little bit jumping up and down on ladders and things like that, and going down and adjusting the fan speeds each time. The first few times it could be time consuming, but I would certainly, and I don't know if many of your webinar participants go solo. I don't know if there's economy doing it with 2 people, but so certainly half a day to get a system balanced and up and running. But there's also a component of educating the homeowner about how the system works and using the controller, setting any away schedules or night flushes or things like that. That's part of the service that we also offer while we're commissioning. So bigger projects where there's a lot of up and down, if the unit is in the basement or the uppermost floor and you've got to go up and down stairs a lot to do these checking, it can take a while. So 6 hours perhaps in a bigger home.
I got a question, John. Does your systems have pressure ports that tell me automatically that I'm balanced or not balanced, even though I may not have my flows correct to the sources? But do you actually have anything that just says, at least I know that the pressures that are moving in and out of the system are at least balanced?
No, and that's because there's just going to be different lengths of that home run tubing, and the fans, while there's a lot of monitoring of temperature streams and the electricity is being supplied to the fans, and a lot of error messages and information you can get from the controller, it just simply doesn't know that it's what those pressures are, as you refer to. So you do have to use a flow hood to check all those. I should point out, without making it more about our system rather than commissioning, is that like a lot of HRVs, there's ways that frost protection can be had. I didn't really talk about what happens when condensate builds up on really cold nights. If it's quite cold, a lot of systems either go into exhaust-only mode or actually redirect the exhaust into the incoming supply airstream. We do not do that whatsoever. We rely on either a ground loop preheater, that's a whole separate device that connects to the HRV and winds up making the unit almost 99% efficient, or an electric resistance preheater to temper that incoming frigid air in Canada so that it's not so bad and doesn't create the conditions that might generate frost in the core. But otherwise, the fans just are independent supply and exhaust fans. When you turn the unit on, it defaults to the middle speed, and you've got to go check those rates, those flow rates. The other thing is that fan is going to go on and maybe push 100 CFM into a silencer out of which there's 10 ports. And if you're only using 8 tubes for your system, just because of the way the design works, you got to put a couple caps in those empty ports. So you really have to check it at the end of the line and figure out what those rates, because a 40-foot run of ducting and a 70-foot run of ducting will have different rates for the same fan speed because of pressure loss, pressure drop.
So another great question was when commissioning, is it recommended to use a pitot tube to measure velocity pressure in order to arrive at the CFM of intake and exhaust? Do you run into that, John?
Well, we use a flow hood, and I think one of our crew has an ASIN. Some are using competitors' devices, which I won't mention, but no, they're not pitot tube style. They're the I'm not sure what you call the name of that. I'm more on the HRV side than the actual device that measures it, but I've done dozens of commissionings with a competitor's flow hood.
Sure.
So,
Sure, you can do. You can use a powered flow hood, which is basically going to create a back pressure that you just kind of use to ramp up that back pressure until it zeroes out the pressure of the fan, and that's how it comes to. That's how it gives you the answer. Those are always going to be limited in their amount or in how far they can go. So, if you as far as the capacity or the volume of air that they can test, or the pressure that they can test. At some point, you need to use a passive flow hood. So when you talk about the ASIN can actually do both. So the ASIN is going to test very, very, very small, very, very small pressures. And let's see if maybe I can show you a picture of that ASIN. This is kind of what it looks like. The ASIN will do will both create back pressure. You can see here that there is actually a fan blowing in. It does not use an exterior or another manometer. This is it actually is a flow meter. It's actually testing flows, and it actually is right here built in. It's got some some onboard storage as well. It's a touchscreen, but this fan is going to create pressure to sort of compete with the pressure that's caused by this fan or by the exhaust or by the pressure that's in that ductwork. At some point, it's going to be overpowered and essentially just stop. And so the ASIN will actually become a passive flow hood and can test all the way up to about Joe? I think it's like 258, something like that, 258 CFM.
No, we can go there. It'll do really close to 3 something, almost 4 as a powered flow hood. And as you go beyond that, it actually combines both and just does an extrapolation. I've actually got it to go 450 as direct readings, and it'll easily read up to easy 650 numbers in the extrapolated mode. And they're trying to actually get rid of the extrapolation. That's the next version that's coming.
Yep, and I want to go back to this one too. Back to the question, or back to the comment about pitot tubes. If you want to use that, if you want to take that route, I want to recommend to you that you check this site out, residentialenergydynamics.com. They have a lot of these free calculation tools built in. And one of them will actually help you to estimate or to get an idea of what kind of pressures and what kind of flows you're getting from a pitot tube and just about anything, any kind of duct. But I do recommend the ASIN in this application, not only because it's light, but also because it's extremely accurate and tests very, very low and very, very high flows. So it's 2 o'clock.
Oh, wait, there's one question
Joe,
I think we should answer.
Joe wants to say something?
Yeah, let's answer one question. So one of the questions that came out, John, is, well, how do you actually measure your system or commission if you're integrating it into the duct system?
We don't commission systems that do that.
That's the answer.
So there's no way to guarantee the performance. And, I don't know how a commissioning agent, even if it is ducted into the system, how they could vouch for, once the house has been sheetrocked and plastered, that the installers of the HVAC system did an accurate job air sealing the ductwork. With our system, it's completely continuous, solid but flexible plastic tubing that mounts to the manifold at the HRV end with O-rings, and therefore it's perfectly airtight, and then is airtight all the way to the register. So we can be sure that there's no air leakage into the wall cavities. And that's why it's a unique system. We sell more than the unit. We sell the ductwork, we sell the controls, and we don't really do commissioning, because if somebody's using a 3-foot wide or 4-foot linear slot diffuser, I'm not quite sure how you get an accurate reading out of that with any instrument I've seen, like the ones that are on the screen right now. So you have to fabricate some cardboard device to get it to work, and it's very hard to do that accurately. Cooking up
point counterpoint.
Now, I guess I'm sure there's systems that compensate for the incredible turbulence that's generated by some of these things, but that's a field condition that I maybe was whipped up in an hour if you keep foam and tape and zip tape in your trunk. But we just feel a lot more confident that you might be able to measure the flow coming out of there in the case of a range hood, but what if the guy didn't put mastic on the ducts? You have no way to know that. So.
Yeah, well, there's no way to isolate your system from theirs, basically.
Not when they're combined, right? Exactly. So, and again, if sometimes the duct is, how when you're moving 12 CFM, when you don't have a call for heating or cooling, how you're doing that through an 8x10 duct, I'm not exactly sure. Does the air ever get there? Don't know.
Well, and one thing you pointed out is you were measuring incredibly low pressures to measure that kind of flow. That's really a challenge all by itself.
Yeah, exactly.
Thank you so much for joining us. And if you have any more questions, or if you're looking for a little bit more information, especially if you're frustrated that you really had some specific goals, or some specific things that you wanted to get out of this webinar, definitely contact me personally, and I'd love to help you out. So that's what we're here for. And thanks again so much, Joe, Chan, signing out. Thank you so much. Have a great week, everybody.